Hello, good people. Let's talk parametric equations. I suspect this might be the first time that you've dealt with parametric equations, but you're going to see they're in a lot of ways they're not too bad. There's maybe going to be a couple challenges we face along the way, but let's get started. If we think about, let's say, a ball being thrown out of somebody's hand at a height of 5 feet, we know the path of that ball, if it's thrown downfield, is going to be a parabola from previous study. And things we might be asked are, what is the furthest, or what is the highest it reaches? And of course that would be the vertex point here, the y value. How far downfield was it when it reached that? That would be x here. How far total did it go? That would involve finding the x. How far horizontally did it go? Those kind of questions. But what if I wanted to know how high was the ball after half a second? I'd have to introduce a time element. And let's say the ball's here, and then I'd have to figure out what x and y are based on that time element. So what we have for parametric equations, t is a parameter, time is a parameter, and f of t, a function of t, gives us an x value. So we can find where the ball is down range after t seconds, and how high up is it after t seconds, and that would give us our xy. So x is a function of t, y is a function of t, and the only difference is that we're going to talk about what's called orientation, and you'll see what I mean by that. So let's go ahead and get started. When we did this in class, one or two of the classes, I just said, hey, why don't you guys just go ahead and try to guess which of these parametric sets of equations, this is a set of parametric equations, which one gives us each of these. And a lot of people, I think most people got this right just based on guessing. We said, well, this is kind of linear and linear, so maybe C. Here we've got, this would be, we'd expect maybe a parabola involved in here, so maybe this. A square root type curve, and square root type curves look like this on their side, so maybe that's it. And here I see we've got some bad values to choose for t, and here we represents a bad value, so they were able to go through that. But here's the way we would do this to get not just, what if we had 6 of these parabola looking things or 6 different lines, how would we know? So here is number 5. We're going to choose a value for t. From that, x is just going to be equal to t, and y is going to be equal to t plus 2, and from that we should be able to get our xy points. So I'm just going to set up this expanded chart here, and I'm only going to pick a couple of points, but if we were graphing it, we might want to pick a bunch. So if I choose t to be 0, x is equal to 0, y is equal to 0 plus 2, and our ordered pair comes from the xy. Worth noting, this 0 is not that 0. This 0 is from the x, because those won't always be the same. And let's pick another point. I'm going to pick 3. Just no particular reason. And I get x equals 3. So my x coordinate is 3, and y equals 3 plus 2, 5. So we've got 3, 5. So I'm looking for, and I'm going to go to where I think it is. It's a line. Does 0, 2 look like it's on there? Yep. Does 3, 5 look like? Yep. 0, 2 is not on here. 0, 2 is not on there. And 0, 2 is not on there. So 5 must be C. So let's continue with 6 here. So for 6, my chart's going to look like this. I choose t, x is equal to t squared, y is equal to t minus 2, and that will give us our xy values. I should do this, t minus 2. And I'm just going to pick a couple of values for this as well. I'm going to choose 0, almost always do, and x equals 0 squared 0, y equals 0 minus 2, negative 2 for 0, negative 2, and then I'm going to pick 2 here. If t is 2, x is 2 squared 4, and y is 2 minus 2, 0, 4, 0. And we look at 6. Well, we suspected maybe that might go with the parabola. Let's see. 0, negative 2, there it is. 4, 0, there it is. So I think that's probably right. Let's check the others to make sure. 0, negative 2 doesn't look like it's on there, and 4, 0 certainly is not on there. 4, 0 is not on here. 0, negative 2. So number 6 is D. For 7, we're going to choose a value for t to figure out that x is square root of t and y is equal to t, and get our xy's from there. So I'm going to choose 0, square root of 0 is 0, y equals t, y equals 0 for an ordered pair of 0, 0. And right now I know it's this, but I'm going to pick another point. I'm going to jump to 4 because 4 is going to be a little bit more convenient than 2 or 3. 1 wouldn't be bad, but I'm going to jump to 4. X is square root of 4, 2, y is 4. 2, 4, we go up and check the one that we thought it might be that looks sort of like a square root on its side graph. And I have 0, 0, yep, that one definitely appears to be on there, and 2, 4 certainly appears realistic that it could be. And so that is B. I'm going to go through the process with 8, even though maybe we know it's A at this time. So I'm going to go through 8. In number 8, we're going to choose a value for t. X is 1 on t. Y is t plus 2. That'll give us our xy coordinates. And then I'm going to talk about the orientation after that. I try to pick 0 and I've got problems. So I'm going to pick 1. I get 1 on 1, 1. I get 1 plus 2, 3. 1, 3 should be on the graph. And I'm going to pick 2, and I get 1/2. 2, I get 4. So 1/2, 4 should appear to be on the graph. Let's take a look. 1, 3 appears like maybe it's on the graph. 1/2 takes me up to 4, and that at least seems reasonable and would not seem reasonable on any of the other graphs. So I am going to say that number 8 is A. Now, let me go back and talk about orientation, because truthfully the author probably should have put orientation on this. And orientation it's an arrow, but it's not an arrow at the end of the curve. That just means the curve goes on forever. The arrow is what is this happening since we're dealing with t time chronologically. What direction is the graph building? So let's look at 5. Number 5, which corresponded to graph C, at 0 we were at 0, 2. And then at time equals 3, we were at 3, 5. So the orientation of the graph is we're moving from bottom to top. So I'm just going to put an arrow in there. Other things you might put in there, you might put a location there. You might put a location at a lot of points. It's like if the moon is orbiting around the Earth. So here's the Earth and here's the moon, and it's orbiting around. What we might want to know is, hey, when is it here? Well, it's here at 3 p.m. You know, so we might have like a 3 p.m. associates to that point. We might have a noon associates, just to give the reader some idea of the speed things are happening and the direction they're happening in. Okay, so if we look at 6, which is graph D, 6 we went from 0, -2, and the next point we got is 4, 0. So we are moving in this direction. You could put it here. We could put a t equals, that would be t equals 2 there. You're just giving the reader some information, but we definitely need some orientation. 7 we decided is graph B. We went from 0, 0 to here. The graph is oriented that direction. And number 8, the first point we found was 1, 1. The next one we found was this way. Our orientation is that direction. And now at some point, I suspect if we have negatives, we should probably put some negatives in and show the direction of this branch as well. And we could put in -1 and -2. And I think we would see that that one is moving this way. But you're welcome to give that a try. Graph is moving this way, I suspect. But by all means, try it. Okay. Now, important, it doesn't show up very well here. They're showing us that the orientation is this way. And I'm going to go through just one of these things, and then I'm going to discuss it kind of from a graphing approach, because what we did in class is we split this up, I believe, and different people tried different problems on here. But this one of these parametrically represents that. So I'm going to go with A. I'm going to give A a try. So what are we going to do here? We're going to choose a value for theta. That's our parameter. We're going to take the cosine of that theta, and then we're going to take 2 minus the cosine of that theta, and that's what x equals. Then we're going to take the theta, we're going to take sine of that theta, we're going to take 3 minus sine of that angle, and that's what y is, and this will give us our xy points that hopefully are on that circle. Well, let's find out. Typically on these, you can get away with just using these points, quadrantals, so 0. Cosine of 0, as we all should remember, is 1. Sine of 0 is 0. 2 minus 1, 1. 3 minus 0, 3. Ordered pair 1, 3. I'm hoping it's on the circle, and it is. Let's continue. Pi on 2. We should know cosine of pi on 2 is 0. 2 minus 0, 2. Sine of pi on 2, we should know it's 1. 3 minus 1, 2. We get the ordered pair, 2, 2. And I see we've got 2, 2. It's on there. However, I'm a little bit concerned that we've only moved a little bit. It appears like we're moving in that direction. If we continue through, and that would be bad. If we continue through this, pi, cosine of pi, negative 1, 2 minus negative 1, 3. Sine of pi, 0. 3 minus 0, 3. We get the point 3, 3. Which is great. It's on the circle. Wrong orientation. And 3 halves pi, cosine is 0. 2 minus 0 is 2. Sine of 3 halves pi is negative 1. 3 minus negative 1 is 4. And we get 2, 4, which is here, but its orientation isn't any good. So here's what I liked about this one. What I've discovered is, take a look. 2, 3 appears to be the center. And then we've got this minus cosine. So of the other choices, the next one I'm probably most likely to look at is this guy right here, because if we quit playing mathematician, play scientist for a minute, it looks like maybe this gives us our center, and then the cosine sine thing maybe give us circles. We just need something in a different direction. So now is a good opportunity for me to go to graphing calculator. I'm going to go into window here. Right now I'm currently set up 0 to 2 pi, and that makes sense for this problem. And these steps could be like 0.1 is fine. I wouldn't want to step by 1 because that's only like 5 steps of the graph. We want to get a lot of points on there so it looks fairly accurate. This would actually work, negative 10 to 10, negative 10 to 10, but since I know that what I'm looking for lies between 0 and 4 and 1 and 5, I think I'm just going to do that. X 0 to 4, y is between 1 and 5. And now I'm going to go into mode, and my mode, our modes are typically in function. I'm going to set it to parametric. And I'm going to go to y equals, and I probably have some other stuff in there already, but I'm going to go to y equals, and I'm just going to clear this. I'm going to leave my other in there for my convenience. Sorry for that muddy, if it muddies up things, but I'm going to enter c into here. So I get 2 plus cosine. Because it's parametric, it oftentimes, whoops, I put that in the wrong spot. I'll come back to that. 2 plus cosine. If I go up to x, t, theta, n, you'd think it might go theta, but parametrics are often based on time, even if the time is the angle. So it gives us a t. And in here I want 3 minus sine. And what's important to do this, we don't want to look away when we're doing this because we need to pick up orientation. We want to make certain that this thing builds like this, in that direction. It doesn't matter where it starts, it has to build in that direction. So when I go to graph, let's see. Uh-oh, I think I know what I did there. I will be right back. Let's go back into mode. Into mode, I'm in radians, and I go back to my window. Oh, you know what? You have a different window for parametrics. Okay, so I want my window to be 0 to 2 pi. I want t to be 0 to 2 pi. I know that. I knew that was the case, but So 2 pi. I'm going to step by 0.1s. I'm going to x min, oh, I like 0 to 4 here, and I like 1 to 5. So some of this was set up nicely. And now I'm going to graph this, carefully watching this. Hopefully we got it here. And we see it builds in the direction we want it to build. And most definitely, we could do a trace. And we see we're at 3, 3. And as I trace over, got to trace over here a little bit. Doesn't know whether to trace right or left. There we go. You can see over here, it looks like we're at 2, 2, etc. So I think it's C. C's our solution. We could get that by going through this, but that's a whole lot to do of guess and check. All right, let's continue on. Sketching curves. So here we're going to sketch a curve, and then eventually we're going to eliminate the parameter. And our parameter here is t. We want to get rid of t. And that's really what I'm most concerned on this, but we'll go through some of the sketching curves. So just like we did before, we're going to choose a value for t. I'm going to say x equals the absolute value of t minus 1. We'll do that in our head. Y equals t plus 2, and that should give me my xy coordinates. And I'm going to pick a few here, but I'm going to take a look and see what value should I pick. I don't just not necessarily go 0, although oftentimes we will. I definitely want to build around 1, because as t changes from 1 to a little bigger and little lower, that engages the absolute value thing. So I'm going to put 0 in. 0 minus 1, negative 1, absolute value 1. 0 plus 2, 2, ordered pair 1, 2. I'm going to put in 1. I get 0, I get 3, 0, 3. I'm going to put in 2. I get 1. I get 4, 2, 4. Or 1, 4, excuse me, 1, 4. I put in 3. I get 2. I get 5, 3, 5. I'm going to graph that and see, because I know I've got my most interesting value. Maybe that's all I'm going to need to get a feel for what's going on. So let's see. My x values are always to the right. My y values, I believe, might be able to go down. Let's see. So x, if I go 1, 2, 3, maybe 1, 2, 3, 4, 5, 6, maybe. So I've got a point at 1, 2. And that's when t is 0. And then my next point is at 0, 3. At that time right now, you probably could put an arrow in, but we don't know whether it's a curve. But we can put an arrow between here and here when we join them. We got a point at 1, 4. We've got a point at 2, 5, or 3, 5, excuse me. Nope, 2, 5. That's bad. Here and here. 2, 5. And there's nothing for me to believe that anything more interesting or weird is going to happen after that, because we've already found when x shifts from, or when t minus 1 shifts from positive to negative. So I believe this thing's going to look like this. We have a slope. We're down 1 over 1, down 1 over 1, down 1 over 1. I think we're going to look like that. But as we stated earlier, our orientation is there. And maybe you want to put a t equals 0 there. And maybe you want to put a t equals 3 here, just to give them some kind of feel for this graph. Okay. You'll see this kind of thing quite a bit. This is a lot like what we just did on the example on the previous page here, where we've got an x associating to cosine and a y associating to sine. So you might want to even try to predict what this was. We had a circle on the previous page. So here we go. Oh, I got to eliminate the parameter. Thanks. I heard somebody out there in computer land yelling to me, on the internet land yelling to me, eliminate the parameter. So to eliminate the parameter, what you would like to do is find an easy t to solve for. And it's easiest to solve for this t right here. So y equals t plus 2 gets us to here. We get t equals, subtract 2 from y minus 2. And you'll hear me say this a lot. If y equals 2, then, if t equals y minus 2, then t may be replaced by y minus 2. So that would be x equals absolute value t replaced by y minus 2. Minus 1 gives me x equals absolute value y minus 3. So x is a function of y, but y is not a function of x. Okay, now here we go. This one's got a lot going on when we get to it's a really good problem, but we don't want to write big on this one. I'm going to choose a value for theta. X is cosine of theta. Y is 4 times sine of theta. And then we're going to have our xy's. And I'm going to pick quadrantal angles. 0. Cosine of 0, 1. Sine of 0, 0 times 4, 0. 1, 0. Pi on 2. Cosine of pi on 2 is 0. Sine of pi on 2 is 1 times 4, 4, 0, 4. Cosine of pi, negative 1. Sine of pi, 0 times 4, 0, negative 1, 0. And 3 halves pi. Cosine of 3 halves pi, 0. Sine of 3 halves pi, negative 1, negative 4, 0, negative 4. And I know by the time I get around to 2 pi, I'm back to the same as entering 0. So let's sketch that. I'm at 1, 0. I'm at 0, 4. I'm at negative 1, 0. I'm at 0, negative 4. And I think our instincts are probably right if we assume maybe that is an ellipse. But we're going to prove that it is in just a moment here. In fact, if it is an ellipse, I would hope we all know this. HK 0, 0, this is an x squared on. We moved 1 right and left. Plus y squared on, we moved 4 up and down. Y squared on 4 squared 16 equals 1. Wonder if that's what this is. Let's eliminate the parameter. Now, this is a little bit challenging here. To eliminate the parameter's theta, I have to solve for theta. I'm going to solve for this theta right here. And I get from x equals cosine of theta. How do I get rid of cosine? I have to take cosine inverse of both sides. So cosine inverse of x equals theta, which means cosine inverse of x theta may be replaced with cosine inverse of x. So I get 4 times sine of cosine inverse. And a little heartbreaking in class the other day when I asked what goes into inverse trig functions, but I understand. I probably forgot stuff too when I was a junior sitting in this class. So cosine inverse, what goes into inverse trig functions? Well, what just goes into a trig function like sine? What we put into there is an angle measure. What comes out of there is a ratio. It's y on r ratio. Ratio of side lengths. So this x, what's going in here is a ratio of side lengths, and I'm going to write it as x on 1. So 4 sine of cosine inverse is what y is equal to. All right. But this is an angle right here. This guy right here is an angle. I'm going to call it angle fish, and I'm going to build angle fish. Angle fish is the angle that produces a cosine ratio x on r of x to 1. X to 1. That's fish right there. But I want sine of fish, and sine of fish would be this side length on this side length. A little Pythagorean work. 1 minus x squared's square root is the y value. So y is 4 times sine of fish. Sine of fish is this on 1, so just square root 1 minus x squared on 1 if you like. And that's great, we got it, but back to my question. I wonder if this is the same as that. I'm going to square both sides. Y squared is 16 times 1 minus x squared. I'm going to distribute 16. Y squared is 16 minus 16x squared. I'm going to group my x's and y's together. 16x squared joins a plus y squared equals 16. And when I divide everything by 16, take a look. Sure enough, this is an ellipse. It would fit that because there's our rectangular, ends up equaling that. All right, 28. On your problems 25 and 27 in the assignment, I'm not going to require you to draw the graph, but we are going to eliminate the parameter. Okay? So I want to pick a t that's easy to solve for here. I suspect maybe this one would be tempting. So I'm going to go t squared equals y on 2. And then we would say that t equals plus or minus square root of y on square root of 2. And then I want to think about that one for just a minute. As I look up here, I can put any value I want in for t. Zeros, positives, negatives. Over here, though, I can't take ln of 0, and I can't take ln of a negative. So the only acceptable values for t are when t is positive. So I'm going to remove that little negative. T is just square root of y on 2, which if we like becomes square root of 2y on 2. And now since t equals square root of 2y on 2, t may be replaced with square root of 2y on 2. And we get x equals ln 2 times square root of 2y on 2, or x equals ln square root of 2y, but that could be written as 2y to the 1/2, and if you remember your logarithm work, you'd know why we do that, because we can pull that 1/2 out in front. Now, truthfully, our work is done. We've eliminated the parameter, but we oftentimes want to try to solve for y, and there's an interesting logarithmic discussion in doing this. So I'm going to go x equals 1/2 ln 2y, or 2x equals ln 2y. And now I need to get this 2y out of here. Well, for that, we need definition of a log. And this is one that a lot of people in class remember. The definition of a logarithm is the exponent that turns the base into the argument. In this case, this is the exponent that turns e into 2y, but this is equal to 2x. So 2x is the exponent that turns e into 2y. E to the 2x. So y equals e to the 2x on 2. And believe it or not, if you took this in regular rectangular mode on your calculator as a function and entered that as a function, and then you went parametrically and entered this, you would get identical graphs. But graphing this one by hand, that's kind of a mess because we got to put in values of e, and it's really a little bit over the top. Okay, in exercise 29 through 34, yay, we get to use a graphing calculator to graph the curve represented by the parametric equations. What do you think the graph of this is? It's a lot like the problems back on that first page, but we've got those coefficients in front of cosine and sine, and then we've got some of these numbers in front as well. Wouldn't be unreasonable to suspect that this is a ellipse, but not centered at the origin. Well, let's go ahead and find out. Then we can play scientist. I'm going to go back into window. I think I'm going to, just because I don't know exactly where this is going to appear, even though I think maybe it's to the right and down, I'm going to go x min negative 10, x max 10, y min negative 10, y max 10. And now we're going to go in here and we're going to change these guys. So I guess I could clear all of this stuff out, but I'm only going to be graphing the first ones anyway. So we have 4 plus 3 cosine t and negative 2 plus 2 cosine or sine of sine. You'll see that typically sine goes with y, and that's because sine has a y in it, y on r. Cosine is x on r. Cosine typically goes with x. But let's go ahead and graph this. We're going to get the orientation as it happens. And there's our orientation, and it appears like everything is down. I didn't need that much room up. And it looks like it's all compressed by negative 4. And by the time we get over to 7 here, and it appears like the center of this ellipse is at 4, negative 2. And from there, it looks like we go to the right 3, down left 3. and up 2, down 2. And I'd like to suggest that that would make this very predictable what's going on here. We went to the right 3, left 3. We went up 2, down 2. We went to the center at 4, negative 2. That's a pretty darn good way. Sorry about that. Didn't have that centered. But you can see it on the graph here. That's a pretty darn efficient way to write equations of ellipses. Here's our center, 4, negative 2. This is actually our A value, our B value. We don't even have to deal with A squared, B squared. Okay, secant tangent, y equals, let's clear this. And for secant, 1 divided by cosine t. For tangent, tangent. Oh, I need to go back. What was our orientation back here? I'd like to go back and do that, but I'm going to get the orientation on this one. So let's do this graph, and we're going to follow the orientation. We're going to pay attention to it. 1 does not like that. Let's go back into y equals, and let's figure out what it doesn't like about that. It doesn't like that I didn't have a t here. Now we graph this thing. Ooh, and we see that things happen pretty darn fast there. So if things happen too fast to kind of get a feel for what the orientation was, one way to slow it down is to go into your window and choose smaller steps of t. I'm going to go 0.02. I'm going to make it create more points. So I did recognize, and maybe you didn't recognize all of this, but I've done this problem before. I did recognize it appears to be a hyperbola and hit these values right in here. But let's go ahead and take a look and get the orientation. So we graph that guy, and there it is. And so it goes up, comes down, then comes back around. So hyperbola looking thing, which turns into pretty much straight lines pretty quickly. Hyperbola looking thing. It didn't truthfully draw the asymptotes for us, but you can suggest it did. It really tried to, it went out this direction first. When it got off the screen and started again, it jumped down to here and just tried to connect the dots. And then it went this way, and when it got on here, it just continued like that. So there's our orientation. You could do this. It started 1 on this curve, jumped to 2 on this curve, and then jumped to 3 on that curve. Here's where t was 0. That's where it started. Okay. All right, let's take a look. 34. 34 is on here. It's just a bit of a mess, and I just wanted to show you things don't always end up so neat and pretty here. Let's go ahead and enter these. Clear and clear. We need 10 minus 0.01 second e to the t, and we need 0.4 t squared. And I'm going to keep it in that same domain, and we're going to take a look at this thing, and well, that's pretty ugly. It does seem to really like being over at 10 here. So I'm just going to play around for a little bit. I'm going to go window. Let's go beyond 10 and see what happens. I'm going to go to 15. If I graph this, boy, it loves being at 10. In fact, it looks like it's at 10, 0. As t gets bigger. Now maybe I want to set my window, because we're trying to determine, I'm going to come back and talk about vertical line tests, but I'm just getting the graphs right now. So we're just trying to determine what the graph looks like, and it seems like it goes up forever, and it might just stop at 10, and maybe it might have something to do with this. Let's think about that for a moment. As t gets really big here, we get minus 0.01 times a really big number. We get 10 minus 0.01 times a really big number. So if I put in, what's going to happen if I put in 1,000 here? I get 0.01 times e to the 1,000th. Starts reducing this quite a bit. I think this thing traces down further. I don't think it just stops at 0. I think it keeps going down. Anyway, as we put in bigger and bigger, or bigger numbers to the left, we can start thinking in terms of the left. But let's take a look at this. Let's go window. Let's go Y max. Let's go Y max 100. Graph that thing. Still seems to like 10. and we continue on for a while. My biggest problem here is in my window I didn't let t be big enough, and really if we look at it, 6.28 doesn't necessarily make a whole lot of sense. This 0 maybe doesn't even make a whole lot of sense. Let me go negative 50 to 50. See what happens in here, and we graph that. And it's going to take a while. I could have used smaller steps. I sure wish I would have now, because this is normally where I would turn on music, but copyright laws will prevent me from doing that right now. And this is trying to go through a whole lot of tiny little steps, and I would love to just be able to disable this thing right now. What if I go second off? It won't like it. It did stop working. I'm going to go back into my window, and I'm going to step by ones. That was a mistake. Let's graph this guy. Okay. This, I believe, is a hyperbola. I believe it's representing this thing as a hyperbola right here. It looks like the graph looks something like, and it does seem like 10's kind of interesting, but I'm going to claim, you can check me on this, if, let's say that's 10, that this thing's hyperbolic, and you can zoom in, zoom out. But I believe we have a graph that looks like that, and I just wanted to show you sometimes we don't get a nice, neat little picture. We have to go searching. So, is this a function of y and x? Is this a normal function? No, vertical line test passes. Not a function. Not a function. And yes, I believe it is a function. But dot, 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 you may need to explore that a little bit more and see, maybe if we look far enough down, this thing wraps back or something like that. We've certainly found out that parametrics do not have to be functions, even though we can graph them. Okay, I have time for one more of these problems, and then I'll have a abbreviated part 2 to this. In 35 and 36, determine how the plane curves differ from each other. And in class, what we did here is we graphed these guys, and that's why I've saved some of this on here. Here's my, I've already got equation B in here, and I've got equation C in here and equation D in here. So I'm just going to reset equation A, and I've got 2 square root t, and I've got 4 minus square root t. And if I graph that one, ooh, I'm going to go zoom standard. Let's try zoom standard. If I've got that one, it looks like I have part of a line. And maybe I need to have t values be bigger, but I'm going to go ahead and go back to y equals. I'm going to turn this one off, and I'm going to graph this second one. And this appears to be part of the same line. I think I'm struggling with, yep, tiny little t values again. It went back to here. So I'm going to go negative 50 to 50, and I think I'm just going to count by ones because it looks like we might have lines here. And let's do that. Okay. Second one, I've got a whole lot more of the line. Let's go back to the first one with these on. We'll put this turned on. I didn't want to clear that. That's okay, we're good. Enter and turn this second one off, and we graph that. But I still only have line going to the right. Well, let's take a look. That line's going to the right because t can't be less than 0 here. And if t is less than 0, or if t is 0, x is 0. If t is 0, y is 4. 2, 4 looks like or 0, 4 looks like a starting point for me. But I think if I zoom to the left, it's going to go on forever. Okay, back to the second one. Y equals. Turn this one off. Turn this one on. And graph. And it looks like maybe the same line, but it stops, and that might be hard to figure out why it stops somewhere, because we can put any value in for t, and that's the answer to the question. We can put any value in for t we want, maybe negative 200 to 200, and graph that thing. It's going to take a little bit longer. I could make bigger steps on here. Probably wish I would have, but it appears like it's going to go on forever because I can pick any value I want for t. In here, I think I can pick any value I want for t. I'm going to claim C looks just like D. Let's take a look. Y equals. Turn this one off. Then I'm going to tell you why they all look the same. Yep, looks the same. It was easier calculations for the computer too, or for the calculator. And then I'm going to go to D. Y equals, turn that one off, turn that one on, and as you can see, we've got the same function. And graph that one. Part of the line, but it looks like x can only be negative. Well, take a look. As I pick values for t, x can only be negative. Now, I'm going to eliminate the parameter in C, and I'm going to be done with this. But if you went through the eliminating the parameter process in each of these, we would end up getting the same thing. So for this one, I'm going to get, if y equals 3 minus t, then t equals, add t, subtract y, 3 minus y. And if I put that in here, I get 2 times 3 minus y plus 1. I get 2 times 4 minus y. I get x equals 8 minus 2y. I'm going to solve that for y just for the heck of it. 2y equals, subtract an x, joins a plus 8, and y equals negative 1/2 x plus 4. Let's go back to our graph. This appears like, in fact, I'm going to go back to graph 1. I'm going to turn this one on. Actually, I'm just going to have them both on at the same time. So it's just going to add the second graph to it. So same line, appears to have a y-intercept of 4 and a slope of negative 8. And if we eliminated the parameters in each of these, they would all end up, we could get to that point with all of these. And then we have to go back and we have to say, hey, what values can t be? What values can x be when I put values for t? Well, x can only be a negative times either 0 or a positive. X can only be negative on that. So these all differ from each other. They're all the same line, but they all have different domains and ranges, and you can explore that. I'm pretty much out of time at this point, but you can explore that. I will do the first one. The first one was the blue graph. So we would say A, the domain is 0 to infinity, it appears, and the range is up 4, or from negative infinity up to 4. Whereas this graph right here, which one was that? That was the fourth graph, I believe. Yep, that was the fourth graph. This graph right here, the fourth, D, has domain negative infinity until 0. And range 4 up to infinity. That's how they differ. Otherwise, they're all the same line. We see that's hard to distinguish. We have a pink curve down to here, and then a blue curve down after that. So appreciate it, and we have a very, very short little problem to work with after that. Probably create a video for that, but it's a very, very simple little problem that we can also address in class. Good luck. Let me know what I can help you with.